I'd like to talk to you about collecting data from custom sensors. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of ML tasks, from regression to vibration and sound classification to object detection and predictive maintenance. You can import data from any sensor and deploy your model to almost any device. You maintain control of the data and firmware the whole time. The Edge Impulse Studio is an online platform that handles everything, including data collection from your embedded sensors, labeling the data, performing any pre-processing calculations, and training machine learning models. This end-to-end project is known as an impulse. You can then test your impulse on live data with a connected sensor. After, the studio will guide you through the process of creating firmware or a library that will run your impulse on any number of platforms. This includes your pre-processing code, trained neural network, and any anomaly detection code you may have so that you can perform inference locally without an internet connection. Collecting data is one of the most important aspects of creating any machine learning project. With Edge Impulse, there are a few ways to do this. The ways you might be familiar with if you've followed along with any of these other micro sessions is connecting your development board directly to Edge Impulse. And to do that, you first upload a pre-built firmware to that board, and note that it is unique to that particular board. In this case, I'm showing you an example of the firmware that's to be uploaded to the Arduino Nano 33 BLE Sense. You then connect your board, in this case the Arduino, to your computer, and that provides a connection to the Edge Impulse Studio. But in order to provide that connection, you have to run the Edge Impulse daemon inside of a command line prompt. The nice thing about this is that once you have everything set up, the process is really easy. You just follow the steps in the Edge Impulse Studio and it walks you through collecting data from your sensors. However, there are a few limitations. First of all, you must maintain that USB connection, which limits your ability to, say, deploy your data collection device in the field to collect data without any sort of connection. You also have limited sensor options. In the case of the Arduino Nano 33 BLE Sense, you've got an accelerometer, gyroscope, magnetometer, temperature, humidity, pressure, I think there's a gesture sensor and a light sensor, maybe a couple of others. So if you wanted to bring in a custom sensor that was not one of those already on the board, you can't do that using this method. You are also limited in a number of board options. If the pre-built firmware doesn't exist, or if the board is not officially supported by Edge Impulse, this option's not going to work. But for the boards that are supported and for the supported sensors, it's great. It's easy to use and it gets you up and running, creating machine learning projects very quickly. Another way that's a little more advanced is to use the Edge Impulse data forwarder. This, just like the one we saw, allows you to connect your board to a computer, and it doesn't have to be an officially supported board. You need to write custom firmware that then collects sensor data and sends raw data over the USB to another command line tool known as the data forwarder running on your computer, and this talks to the Edge Impulse Studio to collect data over that USB line and then send it to your studio project. Once again, there are a few limitations. You must maintain that USB connection just like we saw earlier. You do need to write some custom firmware to collect data and then send it as comma-separated values over that USB line. This will work with any board and any sensor, as I mentioned. And note that data collection is controlled by the studio side, which means if you want to control it from the board side, this isn't going to work. And what I mean by that is, let's say you want to connect a button to the board to start and stop data collection, which is what I'll show you in this demonstration, you can't use this method. The last method I want to talk about is data collection using comma-separated values files, or CSV files. Here, you simply collect all your data in a particular format, in this case the comma-separated values format, save those files, and then upload those files to the Edge Impulse Studio. Once again, you need to write custom firmware to make this happen. Note that this allows you a variety of ways to collect data. Let's say you want to deploy your board to the field. You can do that by collecting on, say, an SD card or transmitting them wirelessly to some other device, like say a Raspberry Pi that sits in the field, collects the data, and then stores them in CSV files. You can also connect using USB and have your computer store the CSV files, which is what I'll show you how to do, as that's probably the easiest approach to demonstrate this. You can use any board and any sensor, you just have to write custom firmware to collect data and store that data on these CSV files. The advantage of this is that you have complete control over the collection process, but it is a little more involved in how you go about it. Note that this won't work for things like images, and it probably is not going to work for things like audio, as you're better off storing that in WAV files, or for images, you're better off storing them as JPEG or some other image format, converting those and then uploading those to the Edge Impulse Studio. But I'd like to show you where you can go for more information about the data forwarder, and then I'm going to show you a brief demonstration using the CSV files. I want to thank IoT Central for hosting this workshop. You can find more workshops and Edge Impulse microsessions at iotcentral.io, where this video will also be available on demand starting tomorrow. If you have any questions about Edge Impulse, or you'd like to show us something you've built with Edge Machine Learning, please create a post at forum.edgeimpulse.com. If you head to docs.edgeimpulse.com, you'll get to our documentation page. Scroll down to find the documentation for our command line interface, or CLI tool. Here you'll find the documentation for the data forwarder. This is a great tutorial on how to use the data forwarder if you have the CLI or the Edge Impulse daemon installed. There is a fantastic Arduino example that's very simple. All that it's doing with the Arduino Nano 33BLE Sense is reading the acceleration data and then spitting out the X, Y, and Z converted to meters per second squared over the serial port, and each one of those is separated by a tab. Once you run that, you call the forwarder and it starts to ingest into your project that you've set it up with, much like you would use the daemon to ingest data from your device. But I'm going to show you the more advanced way, which consists of saving things to a CSV file. To start, I'm going to connect a push button to my Arduino Nano 33BLE Sense, and I'm going to connect it to pin 2 of that board, and then the other side I'm going to connect to ground. What I'm trying to do is start the data collection by pushing a button. When I push the button, it will record from the accelerometer and the gyroscope for 1 second, and then send that data out over the serial terminal, or in this case, over serial via USB. I'm trying to train a magic wand. I want to push the button, and I'm going to make a gesture with the board, and that's how I'm going to collect data. So to start, let's bring up our Arduino IDE, or whatever IDE you want to use. And I'm going to copy in some code and explain what's going on. To begin, at the top, I'm going to include the LSM9DS1. That is the Arduino library that controls the IMU, and we're going to get accelerometer and gyroscope data from that. I'm also going to define my button pin and an LED pin. This allows me to turn on an LED to let me know that I'm recording. I also want to define some constants. In this case, I want to be able to convert from G, which is what the raw accelerometer gives me, and I'm going to convert that to meters per second squared. I also want to define the sampling frequency. I want that to be 100 Hertz, and I want the sampling period to be 1 over the sampling frequency. So that should be every 10 milliseconds. Finally, I want to collect 100 samples. So 100 samples at 100 Hertz is a 1 second window. That's how we get that 1 second of sampling. In setup, I'm going to enable my button pin. I'm going to enable the LED. Note that for the Arduino Nano 33BLE Sense, the RGB LEDs are active low, which is why I'm writing high to this LED pin to turn it off. Finally, we're going to start the IMU, and it's not just the accelerometer, it's the accelerometer and the gyroscope. If that fails, we'll just hang here and print a message that hopefully we'll be able to see. In loop, I want to define a number of variables. I'm going to store the x, y, and z of the accelerometer, the x, y, and z of the gyroscope as floating point numbers. I also want a timestamp so that I can make sure that I'm only printing out those raw values every 10 milliseconds. And I want to try to get it to be as close to 10 milliseconds as possible. Next, we're going to wait for that button press. And note that this is a very basic blocking data collection script. I'm literally doing nothing but waiting for that button to press. You can make this non-blocking if you want, but I want this to be as simple as possible to demonstrate what's going on. Once collection begins, we'll turn on the LED, remember that it's active low, and this is going to show that we are recording. Next, we're going to print that header. This is required for the CSV file, for every CSV file that gets ingested into our Edge Impulse Studio project. So in this case, it must begin with a timestamp because it's a time series set of data, and then we have our 6 values from the accelerometer and the gyroscope. Next, I'm going to set up a for loop that's going to record those 100 samples that we show here. And it's going to start the timestamp. It's going to take the current time in milliseconds, and remember that because it's going to help us delay the appropriate amount to get that 100 hertz sampling. Within the loop, I first want to take the timestamp, so again we can hit that target frequency. Then I want to read from the accelerometer and convert all of those values to meters per second squared rather than being in G, or normalized to gravity. Next, I'm going to read the gyroscope data, and this works similar to read acceleration, where I just pass it in my variables and those variables get updated. Finally, I'm going to print that CSV data with the timestamp. So the timestamp is the timestamp, the current timestamp, which we read here, minus the start timestamp, which is what we took just before running this for loop. And so everything that's printed here is relative to what we took before running this loop when we started the collection process. Then we print out the 6 values, each separated by a comma, and that's what makes the comma separated values file work. Then we want to wait just long enough for our sampling period. We constantly look at the millis function, or the output of the millis function, and compare that to our timestamp added to the sampling period in milliseconds. So that was calculated at the top of our code here. And as long as millis is less than those two things combined, it will just sit here doing nothing. When millis is equal to or greater than this, it goes to the top of the for loop again, and it does that 100 times. Next, we want to print an empty line to signal that we are done with recording. Our receiver script is going to look for this empty line, and that's how it knows when it should save and start a new file. Finally, we want to turn off the LED to show that we're done. Note that this isn't necessary, but I do find it helpful to visually see when recording is happening. So I'm going to set the LED pin to high, remember active low, so high means it's off. And then we're going to sit here for a little bit, make sure that the button has been released for a few milliseconds. I'm just going to put a really simple delay 100 in here to make that happen. And that's all we need for our custom sensor data collection. In this case, I'm collecting from an accelerometer and a gyroscope. Note this will work with, ideally, any sensors as long as it's a time series sensor. It can be any number of dimensions or axes, and you can just put the different values together like I'm doing with this accelerometer and gyroscope data. I'm going to select my board, make sure it's the Arduino Nano 33BLE Sense, and I'm going to go to COM6 because that's where my Arduino board enumerated, and I'm going to upload this code. I will hit escape to not save it, and wait just a moment while it compiles everything and uploads to my board. When it's done, you'll want to open a serial monitor. Sometimes the board switches over to a different serial port, so you will need to go to Tools, Port, select the connected serial port, and open the serial monitor again. You shouldn't see anything happen initially, but I'm going to push the button, and you should see it spit out exactly 100 samples over the course of 1 second. You can see the comma-separated values appear here with the header information, and it appears under that. Every time I push this button, a new set of data comes out. What we want to do from here is you can either copy and paste these individually into a CSV file, or we can write a script to automate that collection process for us. I've written a collection script for you to use. If you head to github.com/edgeimpulse/example-data-collection-csv, you can see an example of this CSV data collection. In fact, the Arduino program we just wrote is here under our Arduino examples. And if we go back out at the top, you should see serial data collection CSV. This is the Python script that we're going to use. I won't go into the nitty-gritty details of what's going on here, but note that it is parsing some command line arguments. So this works like a very simple tool that we get to use, a command line tool, and you feed it the port, the baud rate, the directory you want to save the files, and a label. And what we care about is down here. So I'm going to zoom in so you can see this. If you run this file, it will print out the available serial ports, and hopefully that'll give you an idea of what you need to connect to. It's going to parse the arguments, configure the serial port, attempt to connect to the serial port, and this is where the interesting part begins. It's going to set up a serial buffer where it will receive all of this data. It will then create the output directory and then sit here waiting for bytes from the serial port. As long as it sees bytes, it will read those, look for that empty line, and remember that's where that transmitting program we had, it transmits that blank empty line when it's done transmitting all of its raw data. It then strips out any of the extra new lines, converting the return and new line characters to just new line, and then it writes the contents to a file. That's really the basics of what's going on in this receiver code. The other thing is it looks for Control-C so that it closes the serial port nicely before exiting the program. So let's scroll up. We're going to click Raw. We're going to press Control-A, Control-C, or I will do it here. You can copy this. And we're going to open a new file and paste this in. You can also download or clone that repository if you wish, but this is another way to do this. I'm going to save this in my downloads. I'm going to call this CSV receiver.py. So now it's all nicely color-coded as a Python script. I'm going to close out of COM6. Note that I need to do this because otherwise I can't connect to the serial port using Python. So let's close out of that, and I'll minimize Arduino. Let's bring up a command line prompt. Let's go to downloads where I have that file saved. Note that for this file you do need to install PySerial, which is done by python-m pip install PySerial. You'll want to wait a moment while that installs. It's already installed for me. Check your Python version. I'm running 3.10. This should really work with anything above Python 3. So I'm going to say like above Python 3.5. So now I'm going to call Python CSV receiver.py. If I run it, it's not going to do much. It's going to say I need to call it with these particular arguments. And note that it does give you the available serial ports. So from here, I'm going to call Python CSV receiver.py. -p is my port number, or port designator, in this case COM6 for me. Baud rate is 115200, that's what we set in the Arduino program. Directory, I'm going to call this wand. It's going to create that directory in my downloads directory. And let's do a label, I'll call it alpha. Now we're going to run this, and it's listening on that serial port. So I'm going to take my wand here, I'm going to push the button, and I'm going to draw, I'm going to call it an alpha. So I'm just going to draw an alpha in the air with this breadboard of a magic wand. So here we go. Push button, draw it. And as you can see, it wrote data to the wand directory alpha, which is the label, dot some unique identifier, dot CSV. And we would continue this ad nauseum for this particular label. And we keep going with that. When we're done, we press Control C. If you want to change the label to collect something else, just change that label. Call the script again, change the label to beta. So now I'm going to draw a beta in the air, which is a different label. And you would do this, I don't know, a few hundred times or a few thousand times to collect your data. Once we're done, we'll press Control C, and we'll go take a look at our data. In my downloads directory, you can see that wand has been created. If we go in there, you'll see a bunch of alpha files and you'll see a bunch of beta files. Those were the CSV files we just collected and created. And now we can upload these to our Edge Impulse Studio. Feel free to open them and look at them. You can see it looks just like the data we were transmitting to the serial monitor in our Arduino IDE. For Edge Impulse, it expects a header at the top. It expects a column very specifically labeled timestamp. That timestamp column should be timestamp in milliseconds, so you can see it counting up in milliseconds here, followed by each row is all of the axes or the dimensions or the data from these sensors at that time. And we continue like that for the full 1 second window. If you have non-time series data, so for example, you just want one instance of accelerometer XYZ and one instance of gyroscope XYZ, it's not related to time, there's no real motion, this could be useful for things like gas sensors where time isn't really important. You can leave off the timestamp column, but anytime you have more than one row, you're going to need that. So if you are not doing time series and you leave off timestamp, you can only have one row or you'll receive an error in Edge Impulse. So for now, let's keep the timestamp in here as we upload these to our project. Let's go to edgeimpulse.com, create an account if you don't already have one, click Login. Let's create a new project. This is my Magic Wand collection demo, so I'll create a new project here. I don't need to do that. Let's go to Data Acquisition, and we're going to click Upload Existing Data. I'm going to select Files. As you can see, CSV is one of the supported formats, so let's choose Files. Let's go to Downloads. Let's go to our Wand directory, and we'll highlight all of these. The file names, as I mentioned earlier, are very specific. The label comes first as a prefix, then a period, then some sort of unique identifier, followed by the .csv. If you name your files in that format, Edge Impulse will read those in and know how to appropriately label all of the files based on that prefix. So let's open. I recommend letting it automatically split between training and testing and infer the label from the file name. That's that prefix I just showed you. So click Begin Upload. In just a second, it will finish uploading all of the files. In a real situation, you'd have hundreds or thousands of files. When it's done, you can go back to training data, and voila! We have beta and alpha as our labels. You can see those listed here. You can click on them and see my accelerometer and gyroscope data over time. And if we go to test data, some of that data should have been splitted off. Because I chose 20%, it didn't capture them all. And this is part of the reason you want hundreds or thousands of data samples so that it will appropriately split off 20% of your data so you can have something to test with. This is not a great situation. Like I mentioned, you'd have hundreds or thousands of these. I hope this helps you get started collecting data from custom sensors using your own board, saving that information to comma-separated values files or CSV files, and then uploading that information in those files to an Edge Impulse project.